Today we have very interesting topic of design of environmental structures. Let's go. What is the objective of today's webinar? Primary focus of this webinar is to attract the students or fresh graduates who want to learn more about civil and structural engineering. Basically, we'll be giving them some introduction about underground tanks and some details how to model them and what are the considerations which needs to be kept while we are planning these structures. Then we'll move to introduction and little brief of elevated tanks. And in the end, we'll have short introduction to welded storage tanks. And in the end, we'll speak about how we can achieve what we are desiring in environmental structures. And specifically in environmental, but overall civil and structural engineering. This is the objectives I already mentioned to all of you. To make fresh graduates familiar with various types of liquid structures, what are the finite element tools available in order to model these tanks and structures. The most important thing is this webinar will try to focus on the practical aspects of learning and designing of environmental structures rather than typical plate and shell theories which you all must have read during your graduation or master levels. Geotechnical engineering information required to proceed for these design. And the most important thing is importance of interdisciplinary coordination. The primary code, international code that deals in the Middle East or in America, rather than American Concrete Institute 318, always whenever you will go for any tank or structure, it will be American Concrete Institute 350-06. So first of all, let's move to definition. What is a liquid retaining structure? It's very easy. A primary, secondary, or tertiary type of structure in any effluent or wastewater or potable water planning and design structure, which is carrying some kind of fuel, some kind of liquid, some kind of gases, that is called a liquid retaining structure. On the right, you must be seeing the preface. This is the preface of ACI 350-06. The title of this code is design of environmental structures. Why they have to create another code in spite of 318, which is for building? The highlighted text that I have mentioned will tell you why. Because they are subjected to different loading, which is unique from buildings, which is more severe, which has tight serviceability requirements, which has stronger endurance and appearance requirement. So all these structures which need these things should have been addressed through ACI 350-06. It deals with design, material, and all these things. It includes also the design of spillways, tanks, or anything which is conveying water or any liquid. So primarily, I'll start with underground tanks. The focus of this webinar will be more on underground tanks and structures. We have STP'S whenever you are in India or in Middle East or anywhere. You have waste coming from anything, let's say housing. The housing is big. We have big population. So there are sewage treatment plants, which are sophisticated and the needs planning. There are effluents from housing, from hospitals, which needs to be treated before we will be disposing them anywhere in the nature. We have importable tanks in irrigation networks. We have water transmission pipelines. Let's say water pipeline is going from Delhi to Mumbai, but from anywhere. There must be many things which you need, many tanks, many septic tanks, many boxes to split these things. And in the end, we'll be speaking about fuel tanks, which is related to petroleum products. This is an aerial view of typical sewage treatment plant. You all must be seeing circular and rectangular portions in it. In the next slide, I'll be more explaining these items. Here we go. This is a typical component of STP. On the left, you must be seeing on the above some circular 4 tanks, and down there are longer cylindrical types of tank. All of you as a civil engineer must have read in your graduation, we have primary, we have secondary, and we have sometimes tertiary treatment plants. So all this is showing is secondary and tertiary. Just above this, if you will go on the left, there should be a headworks. The primary purpose of headworks is to remove the grids, and it has chambers to remove anything which is big. I am telling you to have all this in your mind before going to any structural analysis. The headworks will send this sewage water to this cylindrical, which is 4-number cylindrical, which is called aeration tank. Aeration, air will come here and they will keep on moving this and they will further send sewage water from here. This is the secondary treatment. Clarified is the aeration is the secondary treatment process. From aeration, it will go to the circular portion, which is actually conical at the base. That is called clarifier. From clarifier, it will go to sludge drying beds. Or if the sludge is still not treated, you must be seeing a big building above. This is called a filter building. There will be sands here. From the clarifier, the sewage water will be going to this filter, which will have sand and cohesionless soils to further drain it. And then from here, it will go to drying beds. Sometimes, if sewage is too much and the ppm and pH values are not as per required, we will return the sewage flow from the clarifier through a return pump station. The building between the clarifier and aeration tank, you must be seeing a building, concrete building, that is called a pump station building, sometimes return pump sludge. The sludge will be returned again for an again flow process. This is how typical STP works. Here is a typical picture I have taken for my project. On the left, you must be seeing the circular structures I just shown you on the earlier slide. That is called clarifier. You must be seeing the showing the water treatment with bituminous paint. Their coating requirements are different and sewage processes. And on the right, there are sludge drying beds. This is of the same project I did. After clarifier and filter building, the sludge will go to drying beds. So from now, you can see from this picture, these are not structures which you usually come across while you are doing a building design. So their protection requirements are different, their durability requirements are different, their analysis requirements are different. Let's move on. Now, we went from initially from the definition to the physical pictures, and here how we model them in finite element software. This is a typical example of what I did in SAP 2000, which is one of the renowned softwares developed by CSM. On the left, this is not the same aeration tank because this varies from project to project, but this is another aeration tank building. And on the right is the same filter building I showed you. From clarifier sewage water will move to this filter building. You will see so many chambers with a basement there. So you can imagine now, other than even the sewage, the requirements of buildings in the environmental tanks are quite laborious and quite extensive and quite complex. And this filter building needs to be checked from 318 and 350 as well. This is a building which has crane above. This is a building which has basement down. This is a building there are so many chambers to drain this sewage water. This is a building where we have pads. So we have modeled all of them in one SAP 2000 model. The next one is the irrigation tank I showed you in the earlier picture. Even you can see there is a steel bridge, there are stair goings, and there is some scumbers and chambers. So we all can model in FEN modeling everything we need within one umbrella, not like plate and shell bending theories we write in our graduation. This is practical engineering. Now, I would like to tell you, when it comes to structural engineering, this is a fuel tank I did. This is about 5 meters down fuel tank. You can see openings in the tank, but why I want to tell you how to model the behavior of a tank is a good question. When it comes to structural engineering, you can model them in finite element softwares, like a shell structure, like a membrane structure, and like a plate structure. Briefly, I would like to move why I chose them as shell elements. The plate structure, plate element, it can only act to sustain the loads which are out of its plane. If something in plane will cannot sustain, it has zero stiffness in that direction. Because the tank will have the bending in itself, so it needs to work like a plate. Shell is the one thing which has the properties to have like a plate. And similarly, the membrane can only act for in-plane forces, like an arch, like a dome. It doesn't have bending in it. Primarily, axial forces will dominate in that structure. Because axial forces will be developed when the forces will be attacked on the structure, we need something which can attract both the bending and both the axial stiffness of the structure. That's why the tanks or any building like this, like a shell structure. This is a typical example. Same fuel tank I'm showing here, elevation. See, all the dots are matching. This is typical finite element modeling. On the down, I would like to go with the soil in the next slide. On the down, all the soil springs values. How to assign the soil spring values, I'll tell you in the geotechnical slide here. Before proceeding to any project, you need to speak with geotechnical engineer, with process engineer, with HVAC engineer, with environmental specialist. What do you need? Usually geotechnical engineers give you the bearing capacity. No, but you also need the depth of foundation. You also need what is the suitable type of foundation because of this type of soil. Sometimes we will go for ring foundation, especially in elevated fuel tanks and storage tanks. Sometimes the contractor or the client don't need the ring foundation. Because of settlement issues, we'll go for raft foundation. The most important thing out of all of this is net allowable bearing capacity and depth of groundwater table. Groundwater is the one thing which can destroy all of your underground tanks. This is a serviceability consideration, not like buildings which has too many floors, not like buildings which have good ductility, good connection, good stiffness, more weight. So groundwater cannot do anything. But underground tanks sometimes are like cantilever structures, just joined in one direction with each other. So groundwater can uplift all of your structure. I'll tell you in next slides also. Now, if I'll go back to the previous slides, the springs that I have signed, I have taken these values from GEOTECHNICAL. If you will go to Foundation Analysis and Design by famous Joseph E. Bowles, he will tell you for the bearing capacity, if you have bearing capacity, if you will multiply it with 4 and then factor of safety we take 3, we will get how much area springs we will apply for isolated footings. And if you will multiply it with 90, this is a general practical thumb rule, 90 into net allowable bearing capacity is your spring value, area spring value. Now, one thing I would like to tell you further is about net allowable bearing capacity. The difference between net allowable and the difference between gross allowable is net allowable is something where you have removed the overburden and self-weight. Everything is already there. The structure weight is there. The fill weight is there. So don't forget when you will check the bearing capacity, don't compare it with net allowable bearing capacity. You are already putting self-weight of structure in your model. You are already putting soil weights in your combinations. So you should check this in spite of net allowable. You should check the value with gross allowable bearing capacity. So it will be safe. Sometimes if you will check with not net allowable bearing capacity, you will be in problem. Modulus of subgrade reaction is another thing which tells you how this soil will deform under the application of load. This is generally referred from geotechnical reports also. The value is same, I told you, 120 for the raft foundation and 90 for the isolated footings. How many types of structures can we have for structure and civil? We can have aeration tanks, clarifiers, filter buildings, lift station, chlorine tanks, retention ponds, sludge pumps, flow chambers, and walls. Similarly, we can have similar structures, but their coating requirements are different. For potable structures, we have wall chambers, we have lift station, we have irrigation tanks, and we have NBR tanks. The most important thing is interdisciplinary coordination. This is not like a bookish design work in the university. When you will proceed for any civil structural design, what do you need? First of all, for any clarified design, you will be needing the grading levels of that site. Because of before this, you cannot proceed. This will tell you the soil is in cut or is in fill. How much overburden will come on your foundation? What loading will you consider when you will take soil load? How many equipments are there? Like sludge pump station will have maybe 20 pumps. Aeration tank will have odor pipes, will have pumps. So data sheets are required from process departments. These data sheets will tell you what is the size of tank, what is the frequency of this tank, what is the loading of this tank. Many sewer pipelines will be coming. You need to check the invert level of these sewer pipes because you will be making opening details for this. And any level change will destroy all of the septic tank, sewage treatment plant concept. It will not work. Most of the plants are working from gravity. So you need to know what is the level of pipes and ditches there. Sometimes if there is no big area available for the sewage treatment plant, we'll go to make some lift station with a holding tank. At that time, you will be requiring levels for demonstration. Geotechnical investigation reports we have already covered. What do we need from there? This is a typical example what civil and structural guy will be needing from process. This is a tank. You will have on the left 1 ton stock coming. You will be requiring what level he needs here. For example, plus 20.7. Where is the basket screen required? What will be the level of water there? There is a mixer here. What will be the weight of this mixer? How it will rotate? How you want to fix this mixer at the top slab? Normally they are fixed at the top slab. This is small in weight. Important thing is to check there is a jib crane also on the top. Jib crane requirement should be provided from process and mechanical. What should be the size of the jib crane? If there is a person standing there, you should take the live load. He will tell you if he needs grating here or no. If he doesn't need grating here, you will provide in a RCC slab. If he needs grating here, you have to provide. This is where interdisciplinary coordination is very important. This is another picture of irrigation tank. Same you can see the pipes are coming from the left and they are going on the right to irrigation pump station. Sometimes we don't need grating. The mechanical guy, process guy will tell you, I need checker plate here. You have to check where he needs the level, what is the span, what is the thickness, where he needs one pipes to show the openings, where he needs sump. You will see a sump on the right where it is written outlet chamber. In spite of straight line, other than even the slope, there is a sump to collect water here. So this is where the interdisciplinary coordination is very important. Now I'll move on to design consideration. Apart from all this planning, like typical buildings, we have flexure, shear, and tension limit state. But where the structure governs in design in environmental structures is serviceability. Most important and crucial of them is cracking. We have bearing also, sometimes it can overturn also, but the most important, which is stringent criteria, is cracking. Here are primary forces. If you see this is an 8.3 meter tank wall, I'm showing you what loadings can be there. If you'll see on the right, you can see this is a water load triangular distribution of water. In SAP 2000, you can model it very precisely from joint patterns. In spite of rectangular pressure, it will apply you triangular load. On the left of this wall, the same wall is carrying on the left the earth pressure, and on the right groundwater pressure, and on the left surcharge pressure. Sometimes the vehicle is coming just on the top slab, so we have to consider truck loading. Sometimes there are other cranes, we have to consider that cranes. In the next picture, I'll show you again. The same 3.45 meter wall, but top slab is down. So this top slab will have soil load also. It will have live load surcharge also. It will have groundwater load. So we will make the load cases as per the combination of the codes, which will not cancel out each other. The wall should be designed in a way so these effects will be maximized for serviceability and same for strength limit straits. These are the typical combinations from ACI 318 and American Society of Civil Engineers 705, which is governing for all of these for load combinations. First is the load combination for strength, and then is the load combinations for stress or serviceability.